Good evening. On this channel, I guide you to stars and other interesting objects nearby in our galaxy. I'm an AI voice, just so you know, but I hope you like me anyway. Tonight, we'll set our sights on the red dwarf star Lalande 21185, the brightest red dwarf of all in the northern hemisphere, yet only visible through binoculars. This star is situated about 8.3 light-years from the solar system. Lalande 21185 is not just one of the nearest stars to the Sun, it's also one of the more mobile stars in our neighborhood. The star exhibits a high proper motion, which refers to its apparent movement across the sky relative to more distant background stars. Specifically, Lalande 21185 has a proper motion of about 4.78 arcseconds per year, placing it among the stars with the highest known proper motions. This means it would take approximately 377 years for Lalande 21185 to move a distance across the sky equivalent to the diameter of the Moon due to its proper motion. In space, Lalande 21185 is moving towards the solar system at a radial velocity of approximately 85.11 kilometers per second. Radial velocity is the component of a star's motion that is directed toward or away from the observer on Earth, measured by the Doppler shift in the star's spectrum. In astronomy, radial velocity is positive when an object is moving away from us, red-shifted, and negative when it is moving towards us, blue-shifted. So, with a radial velocity of minus 85.11 kilometers per s, Lalande 21185 is currently moving towards us, and will get closer before it will start to move away again. Approximately 19,900 years from now, Lalande 21185 will make its closest approach to the Sun, coming within about 4.65 light-years of our solar system, just over half its current distance. Lalande 21185 was first catalogued by the French astronomer Jérôme Lalande in 1801 as part of his comprehensive star catalogue, Histoire Céleste Française. In this catalogue, it was given the designation Lalande 21185, a number that refers to its position in Lalande's list of stars. This designation has remained the most commonly used name for the star, making it one of the few stars that are still widely referred to by their Lalande catalogue number. In addition to its Lalande designation, the star is also known by several other names. It's listed as BD plus 362147 in the Bonner-Dirk-Musterung catalogue, a 19th-century star catalogue that aimed to systematically chart stars across the sky. The BD prefix refers to this catalogue, and the numbers indicate the star's position in terms of right ascension and declination, with the 36 inches indicating its location in a band of the sky centered around plus 36 degrees declination. Lalande 21185 is also designated as Gliese 411 in the Gliese catalogue of nearby stars, which is particularly significant for stars within about 25 parsecs, roughly 82 light-years, of Earth. This catalogue is widely used by astronomers studying nearby stars, making Gliese 411 inches another common name for this star in scientific literature. Additionally, the star is listed as HD 95735 in the Henry Draper catalogue, which is a well-known catalogue of stars that includes spectral classifications. The HD prefix is associated with this catalogue, which has been a key resource in stellar spectroscopy since its creation in the early 20th century. Lalande 21185's motion through the sky caught the attention of Friedrich Wilhelm Argelander in 1857, who noted its high proper motion, meaning it appeared to move more rapidly across the sky than most stars. This discovery earned the star the occasional nickname Argelander's second star, his first being the similarly fast-moving Groombridge 1830. But it wasn't just its movement that intrigued astronomers. Its proximity was also a significant discovery. Friedrich August Theodor Winnecke measured its parallax, the apparent shift in the star's position due to Earth's movement around the Sun, in 1857–58, confirming that Lalande 21185 was one of the closest stars to our solar system. For a time, it was the second closest known star system, only behind Alpha Centauri, until even closer stars like Barnard's star and Wolf 359 were discovered in the early 20th century. Lalande 21185 is located in the constellation of Ursa Major, a region of the sky most famous for containing the Big Dipper. To locate it, one would need to find the Big Dipper and then look slightly southward towards the tail of the Great Bear. More specifically, it is located just northeast of Alula Borealis, or northwest of 46 Leonis Minoris, also named Precipua. The area of the sky where Lalande 21185 resides is relatively sparse, not filled with the dense star fields found closer to the Milky Way's center. Lalande 21185 has an apparent magnitude of 7.5, which means it is too faint to be seen with the naked eye under normal viewing conditions. The apparent magnitude scale is a measure of a star's brightness as seen from Earth, with lower numbers indicating brighter objects. For context, the brightest stars in the night sky, such as Sirius, have an apparent magnitude around -1.5, while the faintest stars visible to the naked eye under perfect dark sky conditions are around magnitude 6. At magnitude 7.5, Lalande 21185 requires a small telescope or a pair of binoculars to be observed. This faintness is typical of red dwarfs, which, despite being close to Earth, emit much less light than larger, hotter stars like our Sun. The low luminosity of Lalande 21185 is due to its smaller size, lower surface temperature, and the fact that it radiates most of its energy in the infrared spectrum, which is less visible to the human eye. A closer look tells us that Lalande 21185 is a classic example of a red dwarf star, classified as a Type M main sequence star. With about 39% of the Sun's mass and a similar percentage of its radius, Lalande 21185 is much smaller and cooler than our Sun. Its surface temperature is around 3,550 Kelvin, which, while hot by everyday standards, is relatively cool compared to other stars. This coolness means that Lalande 21185 shines with a faint red light, most of which is emitted in the infrared spectrum. In fact, its luminosity is just 2.2% of the Sun's, making it one of the dimmest stars visible with amateur telescopes. Lalande 21185, with its slow consumption of hydrogen, is still in the early stages of its life, despite being several billion years old. Unlike more massive stars, which burn through their nuclear fuel relatively quickly, red dwarfs can shine for trillions of years. It will continue to burn steadily long after more massive stars like our Sun have exhausted their fuel and faded into white dwarfs. Lalande 21185 is listed as a Bi-Draconis type variable star, meaning its brightness fluctuates slightly over time due to spots on its surface and its rotation. These spots are similar to sunspots but are more common and can cover a larger portion of the star's surface. Despite being a variable star, Lalande 21185 is relatively quiet compared to other stars of its type. It emits occasional X-rays, and flares have been observed, but it doesn't display the intense flare activity seen in some other red dwarfs. This relative calmness is somewhat unusual for a star of its kind, which are often known for their strong magnetic fields and violent stellar flares. Lalande 21185, like many red dwarfs, has a relatively slow rotation compared to more massive stars. The rotational period of Lalande 21185 is estimated to be about 56 days. This slow rotation is indicative of its age. Stars generally slow down as they age due to magnetic braking, a process where the star's magnetic field interacts with its stellar wind, gradually carrying away angular momentum and causing the star to spin more slowly over time. Lalande 21185 is considered to be an older star, with estimates suggesting an age of about 8 billion years. This estimate is consistent with its slow rotation rate and its relatively low level of stellar activity. While red dwarfs can remain on the main sequence for trillions of years due to their slow hydrogen fusion rates, Lalande 21185 has likely been shining steadily for much of the galaxy's history. Its advanced age is also suggested by its stable, relatively quiet magnetic activity compared to younger, more active red dwarfs. Metallicity refers to the proportion of elements heavier than hydrogen and helium in a star, often compared to the Sun. The metallicity of Lalande 21185 is slightly lower than that of the Sun, with an estimated FeH value of around -0.20. This means that the star has about 63% of the Sun's iron abundance, indicating that it formed in a region of the galaxy that had been enriched by previous generations of stars, but not to the same extent as the region where the Sun formed. A lower metallicity suggests that Lalande 21185 is part of an older stellar population, consistent with its age and position in the galaxy's disk. Lalande 21185 has a high surface gravity compared to the Sun, a characteristic typical of red dwarfs. With a mass about 39% that of the Sun but a much smaller radius, the star's gravity at its surface is significantly stronger. The surface gravity of Lalande 21185 is estimated to be about 65 times greater than the gravity on Earth, log G 4.8 cgs. All in all, the mentioned aspects of Lalande 21185, its slow rotation, advanced age, moderate metallicity, and high surface gravity, combine to paint a picture of a stable, older red dwarf that has long passed the more active phases of its stellar evolution. Its characteristics make it an interesting subject of study, particularly in understanding the long-term evolution of low-mass stars and their planetary systems. The search for planets around Lalande 21185 has a long and somewhat controversial history. In the mid-20th century, astronomer Peter van de Kamp famously claimed to have discovered a planetary system around this star, based on observations made with photographic plates. However, these claims were later debunked when it was found that the telescope itself had mechanical issues that skewed the data. In the 1990s, George Gatewood, another prominent astronomer, also announced the discovery of planets around Lalande 21185 using astrometric techniques. These claims, too, were met with skepticism, as subsequent searches failed to confirm the presence of the proposed planets. It wasn't until the 21st century, with more advanced instruments and techniques, that the first confirmed exoplanets were detected around Lalande 21185, settling the question that had puzzled astronomers for decades. Astronomers have now confirmed the existence of 2 exoplanets orbiting this star, with a third candidate awaiting confirmation. The closest of these planets, Lalande 21185b, is a super-Earth with at least 2.6 times the mass of our planet. It orbits the star every 12.9 days, placing it extremely close to Lalande 21185. Far too close to be within the star's habitable zone, where liquid water could potentially exist. The second confirmed planet, Lalande 21185c, is much more massive, with at least 14 times the mass of Earth. It takes nearly 7.7 years to complete one orbit, making it a distant companion in this system. There's also a possible third planet, Lalande 21185d, which might orbit between the 2 confirmed planets, with a period of about 215 days. While none of these planets are likely to be habitable by human standards, their discovery so close to Earth has sparked significant interest in the search for nearby exoplanets. The star's habitable zone, where conditions might be right for liquid water to exist, lies between 0.11 and 0.24 astronomical units from the star. Although the known planets are outside this range, it's possible that other, yet undetected planets might exist in this region. The research article, The SOFI Search for Northern Extrasolar Planets, 14th, a temperate, Tech-300K, super-Earth around the nearby star Gliese 411, by Diaz et al. In 2019, presents the discovery of a new exoplanet, Gliese 411b, orbiting Gliese 411, as the star often called in scientific papers. The study was conducted using the SOFI spectrograph on the 1.93-meter telescope at the Observatoire de Haute-Provence in France, part of a long-term radial velocity survey targeting nearby low-mass stars. The exoplanet Gliese 411b was detected through periodic variations in the radial velocity of its host star, with a signal that corresponds to a 12.95-day orbital period. The planet is in the paper suggested to have a minimum mass of approximately 3 Earth masses, meaning it is a super-Earth-type planet. It orbits its host star at a distance of about 0.079 AU, which is much closer than Mercury's orbit around the Sun. As a result, the planet receives about 3.5 times the solar insolation that Earth does, leading to an equilibrium temperature estimated between 256 and 350 K, depending on the assumed albedo. Despite its proximity to the star, the equilibrium temperature of Gliese 411b places it in a temperate regime, though it is likely too hot to reside within the traditional habitable zone, where liquid water could exist on its surface. The study's authors suggest that the planet's temperature and orbital distance make it an unlikely candidate for hosting life as we know it. The detection of this exoplanet is significant for several reasons. First, the amplitude of the radial velocity signal was only 1.6 meters per second, making it the lowest amplitude signal detected with the SOFI instrument to date. The researchers conducted an extensive analysis to confirm the planetary origin of the signal, including simulations to rule out the possibility that it was caused by stellar activity or instrumental effects. These simulations considered both correlated and uncorrelated noise, and the results consistently supported the presence of a planet. The study also revisits previous claims of planetary companions around Gliese 411. Notably, a 9.9-day periodic signal reported by Butler et al. 2017 using HIRE's data was not detected in the SOFI observations. The researchers performed an independent analysis of the HIRE's data and found no evidence of the 9.9-day signal, further casting doubt on that earlier claim. Photometric observations conducted alongside the radial velocity measurements also played a crucial role in the study. These observations, taken with the TSUT 30.40M automatic photoelectric telescope at Fairborn Observatory, revealed a stellar rotational period of approximately 56 days for Gliese 411. Knowing the star's rotational period was essential for distinguishing between potential signals caused by stellar activity and those caused by orbiting planets. The 12.95-day signal was found to be distinct from the star's rotation, supporting the conclusion that it is due to a planetary companion rather than stellar activity. Given its proximity to Earth, Gliese 411b is an excellent candidate for follow-up studies. The star's brightness, coupled with the planet's relatively short orbital period, makes it a promising target for transit searches. Although the probability of observing a transit is low, around 2.9%, detecting a transit would provide valuable information about the planet's size and composition. The Transiting Exoplanet Survey Satellite, TESS, and the Characterizing Exoplanet Satellite, CHEOPS, are mentioned as potential instruments for such a search. Even without a detected transit, Gliese 411b's proximity and the brightness of its host star make it an ideal target for atmospheric characterization. The authors highlight the potential of using a combination of high-dispersion spectroscopy and high-contrast imaging to study the planet's atmosphere, a technique that could be feasible with the next generation of 30-meter class telescopes. This approach has been successfully demonstrated on other exoplanets, and Gliese 411b's proximity makes it particularly suitable for such studies. The article concludes by placing Gliese 411b in the broader context of exoplanet research. The planet is one of the closest known temperate exoplanets, second only to Proxima Centauri b in proximity to the solar system. However, unlike Proxima b, Gliese 411b is likely too hot to support liquid water, placing it outside the traditional habitable zone. Nonetheless, its discovery adds to the growing catalog of nearby exoplanets and highlights the potential for future observations that could reveal more about the planet's nature and its atmosphere. Overall, The discovery of Gliese 411b represents a significant achievement in the search for nearby exoplanets and underscores the capabilities of the SOFI spectrograph in detecting low-mass planets around low-mass stars. The study also illustrates the importance of careful data analysis and cross-verification with other instruments to confirm the existence of exoplanets and refine our understanding of their characteristics. In another paper titled Confirmation of the Long-Period Planet Orbiting Gliese 411 and the Detection of a New Planet Candidate by Spencer A. Hurt et al. Of May 2022, a detailed analysis of the planetary system around Gliese 411 is presented. The research was aimed at confirming the existence of a long-period planet, Gliese 411c, and at investigating a newly detected signal that might indicate the presence of an additional planet in the system. The paper notes that various studies over the past few decades have suggested the presence of planetary companions, but confirmation has been elusive. Recent efforts have focused on analyzing radial velocity, RV, data gathered from multiple instruments, including APF, HIRES, SOFI, and CARMENES, to improve the detection of planetary signals. This study utilized high-resolution spectroscopic data collected from the aforementioned major instruments. The authors combined these datasets to perform a comprehensive analysis of Gliese 411's RV variations. Here are the key findings of the study. Confirmation of Gliese 411c. The paper confirms the presence of a Neptune-like planet, Gliese 411c, with a long orbital period of approximately 2,900 days, nearly 8 years. Previous studies had disputed whether this signal was due to a planet or a long-period stellar magnetic cycle. The authors provide evidence supporting the planetary origin of the signal, ruling out stellar activity as the cause. New planet candidate. The study also detects a new signal with a period of around 215 days. Initially dismissed as an instrumental systematic by previous studies, the authors argue that a planetary origin cannot be ruled out. If confirmed, this candidate would have a minimum mass of approximately 3.89 Earth masses and would orbit at a semi-major axis of about 0.514 AU, placing it beyond the outer edge of the habitable zone. Orbital parameters. The paper provides tighter constraints on the orbital parameters of the known planets in the system. Gliese 411b, the innermost planet with a period of 12.9 days, and Gliese 411c have well-defined orbits. The study also suggests that the new candidate may have a low-amplitude signal, making it one of the lowest-amplitude planet detections from the instruments used. Activity metrics and stellar rotation. The authors analyze various stellar activity metrics, including Ha and indices, to isolate the effects of stellar magnetic cycles and rotational modulation on the observed RV signals. They conclude that the long-period signal is unlikely to be caused by magnetic activity, further supporting the existence of Gliese 411c. Prospects for follow-up observations. The paper discusses the potential for follow-up observations to confirm the existence of the candidate planet and further characterize the system. While transit photometry from TESS did not show any transits, the authors suggest that direct imaging with future space missions like the Nancy Grace Roman Telescope could detect Gliese 411c and the candidate planet. Astrometric measurements from Gaia could also provide additional confirmation of these planets. In the coming years, as more powerful telescopes comes online, such as the James Webb Space Telescope, astronomers hope to learn even more about this nearby star and its planets. These observations could provide new insights into the potential habitability of planets around red dwarfs and help us better understand the diversity of planetary systems in our galaxy. If you are still awake and want more content, go ahead and check out our other episodes. And if you want to help create even more, please consider supporting us. While this manuscript was written by AI and read by me, an AI voice, creating this content still required production time from a human being. If you want to support the production, please make a donation to the Milky Way Traveler over at Patreon. To do so, follow the link in the show notes or search for the Milky Way Traveler at Patreon. If anything is incorrect in this episode, if you are missing some information, or if you just want to add your view, feel free to make a comment in the comment section for this episode. Now, thank you for joining this trip, and have a beautiful and wonderful night, with sweet dreams once you get there.